My name is Tyler Harper.
My name is Riley Gagan.
My name is Jacob Budag.
My name is Aaron Houston.
And we are the Electric Sliders. Alright, so, there we go. Oh, we're going backwards. Alright.
It's going to be
Even better.
scrolled down.
There we go. Alright, so our agenda. First, we're going to go over the background for our project, go through the introduction, the design, system architecture diagrams, status of the project, go over a few deliverables and milestones, quick over our budget, and then kind of our conclusion and work for the future.
Alright, a little bit of a background and some rules. So the shuffleboard is a competitive game played by two individuals or two teams in which players will take turns sliding weights, also known as pucks, down a board towards the scoring area at the opposite end of the board. All shots must be delivered from behind the foul line and weights must remain on the board surface without falling into the gutters to remain in play. Once all the weights have been played, the round concludes and the players then walk to the opposite end of the board and prepare for the next round. With a shooting order based on the person who scored the highest the last round, or if no one scores that round, it will be the person who scored previously. And physical contact with the board during shooting is prohibited, and players may not obstruct the weight's path, and no roughhousing.
With those rules, the introduction is pretty much just going to be why we did what we did. We are going to make it a self-scoring shuffleboard, and our goal with it was to bring a new techie era to the game of shuffleboard. I've seen it personally. My my cycling machine in my house has turned into my laundry rack. My shuffleboard at my friend's house has turned into the drink table. It doesn't do anything other than put drinks on it. So our goal with this was to add lights to it, to add a new scoreboard, a self-scoring function, taking something a lot more analog and putting a whole lot of digital into it, bringing life back into it, possibly putting it into some of those new age game rooms that we're talking about.
Scroll to.
Alright, so some of the constraints for our design, obviously cost is a big thing. We are essentially creating a product, or that was the goal for this senior design project. So cost, trying to keep costs down for all of the modules is one of our big ones. I was in charge of the power supply module, so efficiency and reliability were my two main concerns. Making sure that it delivered power to all the modules, there were no hiccups in that delivery, and just doing it as cheaply as possible, and trying to use less parts, not overcomplicate the circuit, make sure that it ran just nice, simple, and sweet.
I was in charge of the sensors module. What we ended up going with in order to score the board was two Logitech C92 Pro cameras. They usually cost around $100 each, but we managed to get it at a good deal at $70, landing us around $140. We shot over on the cameras on purpose, so that we ended up getting a good resolution on the cameras, even if we had a Pi that couldn't necessarily handle that kind of resolution. We managed to drop it down to around 640, 480 for what we were calling for our pixel height and width. Using that was super easy, and we also made sure that we had a microcontroller that could handle 800 milliamps required to charge the cameras.
So I was in charge of the user interface. Of course, cost was a big thing, and as well as the size. How to make sure it was big enough for users to read, and of course, to choose either from a common cathode or a common anode. And in this case, we chose a common cathode based on the circuit we made.
I was in charge of the microcontroller, and the big thing was cost, of course, and we wanted to make sure we had enough USB ports for two cameras, and then for debugging, or coding actually, a mouse and a keyboard. And then we wanted the clock rate to be fast enough to run with the cameras. Okay, so here's our system architecture. So basically, this is the overall view of it. We wanted user input, which is sliding the weights down the board, and power input. And then we wanted to see a score and have lights. Here's a little bit more broad. User input would go to the sensor, which would then give the data to the microcontroller, which gives that data to the user interface to display. And then the input of 120 volts AC would go to the power source and power all 3 modules. So here's the whole flow chart for the entire thing. It's pretty big because we have 3 different modules that use coding. The main one is the biggest of all, which includes all the sensors, the user interface, and then all the scoring. Yeah.
So when it came time for us to run the code, we're not professionals. This is something we're very new to. I personally have never coded in Python before I tried to figure out how to use OpenCV. So a lot of it is very rudimentary and a lot not incredibly efficient, not a whole lot of multi-threading going on. And so we have it all running as one program. We have the microcontroller running the full set. It calls the camera as fast as it can. At the same time, it runs the 7-segment LEDs as fast as it can, which you can see is a mess on the board. That's all I got for that from my movies. Jefferson, question?
All right, so here is a wire diagram for our power module. Up at the top, I started off with we're taking power straight from the outlet at 120 volts AC, and it's being converted to 24 volts DC using a AC to DC converter, a computer charger. From there, we're taking a voltage regulator, going through the scoreboard, the wiring for the scoreboard. We're taking a voltage regulator, bringing it down to 4.5 volts, and then it is going through a series of 2 different gates. The first gates, all the way at the top, are a set of P and N channel MOSFETs, which determines which segment of the 7-segment display has the potential to light up. So if you want a 1, then you turn on 2 of them. The ones for the 1 off to the side. If you wanted a 2, you'd have to turn on different ones. And then the way that we determine which segment actually lights up with a 1 or 2 or whatever else is using a BJT down at the bottom to connect that segment to ground. So for the scoreboard, you're flashing each one of those 8 different displays at 60 times per second. So it is cycling whatever numbers are being called for at 400 times, it's running at 400 times per second. Off to the side, we have our pins for the active throwing light, which tells you which side of the board you should be throwing from, which means that the other side is, of course, recording and tallying up the score. And then down off to the side right here, we have our reset and next round buttons. So the 2 different things that you'd want to do is you obviously, after each round of throwing the weights, you'd want to take the difference of the 2 scores, add that to the total score for whichever side scored the most for that round. And that's what that button would give the command for within the code. And it also flips the active side, so the light and the active camera flip. And then of course the other button resets the game. It sets the total score to 0 and allows you to start playing another round.
So at the end, we struggled through it. We might have done a couple of papers not so great, but we have a fully finished product. It's capable of detecting all 8 pucks on the board at the same time on one side, detecting nothing on the other. It correctly is able to have pucks that are all touching each other without creating an amalgamation by using smaller pixel counts when trying to figure out whether or not an area is detected. And the 7-segment display, while it is flashy, correctly displays, adds up, and scores the board as we're playing. Deliverables and milestones. We've come a long way through this. Not all of our demos were great, not all of them successful, except for Demo 4. Demo 4 was our most and complete success by the end of it. Each individual, all of us had problems along the way for demos 1, 2, and 3. I know I really struggled with color coordination and trying to figure out lighting in a room that changes every single day because of God and Einstein. But overall, we made it to now, and we have a fully finished product.
All right, going over some of our budget. We spent roughly $80 on some of our power components, so that converter, and then some of the regulators and MOSFETs and such. Our sensor components, $186 for the cameras is what it came up to after taxes and all. The Raspberry Pi and the Raspberry Pi cooling fan for the microcontroller. We did not have to purchase the Raspberry Pi, but it would have roughly been about $75. So that module came out to about $90 or so. And then for the rest of it, so the 7-second displays, the material and all that added together, it came up to $729. Of course, if this was mass produced, we would be able to cut that cost down a lot by bulk pricing, and there were a good bit of components that we did not, we either had to buy more than what we needed, or we didn't use all of it.
Okay, so achievements, we did all this stuff through the semester. At the end, we have a fully self-scoring shuffleboard, fully functioning. And we also had 3rd place in the excellence day.
Yep. Man, is this mouse taking up most of our time? There we go.
So some of our expenditure summary, so employee payment, $69,000, power module, $77, sensor module, $186, microcontroller module, $91, user interface, $53. Building materials, we spent around $319, and we had a budget of $1,000, and we were able to manage to spend around $730. Okay. So some of our future work that we're planning to do is add more LED lights, make it more user attractiveness. Some speakers, either users would like to play music or have
Some kind of a video
Some
display
kind-
to show, like, you know when you're bowling and you have like the gutter ball animations? Or you get a strike, you have certain situations like you knock one of their pucks off and it'll be like knockout or something like that to give more of a reactive display to while you're playing. Also, we're planning on adding wireless chargers, and in the future, I'd like to change my code as I get better at it to be able to auto-calibrate to a board instead of it being set to one specific position on a certain size board. And that could be done using the boxes around the size of the board itself with the same color detection that I'm already using now. Alright. Well, that's it.
All right. So, any questions? Yes.
So I know you were saying that, you can't swap it to a different board right now. So what about the detection of the colors? Like, say you lost the pucks and you had to buy new ones. I know it's red and blue pucks. Is it specific red?
It is every color of red and every color of blue that you could put on a spectrum. Every color of red and blue you could put on a spectrum will fit under this thing because we needed to make sure it worked in every lighting that we could put out there.
Yes.
Are there any boards that use red or blue on the background that may interfere with the system? Or that like
In the background, meaning
like the board itself, like the wood that slides on?
Sure.
So for professional boards, whenever people are playing in tournaments, or I've seen them at home, sometimes they'll have the little triangles for red and blue if it's a multi-play game. However, if it's a smaller area than the blue, then it won't be detected by the game.
Sorry, yeah, sure, Dr.
I've
Anthony.
been quiet all night. You said the code is running as fast as it can run.
Not as fast as it can run, as fast as we can get it to run.
So you're not using interrupts?
Reset is
Resets are kind of an
So you're pressing the display, you scan across the display, then you check the camera, then you check the.
That's why it
So
flashes
you're just
away.
alternating in your code as opposed to letting the timer set off to refresh on this place? How do you know it's refreshing at 60 hertz? That's what I want to know. If you don't have a timer or an interrupt.
Yeah, that's what y'all told her to run in the code. Or yeah, that's what we told her to run in the code. So we didn't check it specifically.
How
But
do you check what's running at 600?
yes,
How difficult would it be if you moved this from this shuffleboard table to a different shuffleboard table? How long would it take to recalibrate it? Or even if you took that shuffleboard table and moved it somewhere else, would it be pretty easy to set back up? Would it be?
If you had access to a monitor, keyboard, and mouse, you could recalibrate it in 10 or 12 minutes.
Could I do that, or could you, knowing your code, do that?
It's, if you were able to pull up the code on the Pi, you could change it to.
Okay, so there's no calibration user interface. It's just going into the code and kind of hard coding the threshold.
Correct.
and I mean, if it gets knocked around currently, we have some lines that are drawn there. I would like to either use some form of clamp to clamp it down a little bit better to the board, or possibly an adhesive. For future, you know, if it ever had to be taken off or on, with your permission, which will be asked, I guess, would have been asked tomorrow, we'd like to etch some lines into it so that we know exactly where the arch would be. It would just be small little engraving.
On the rail, not the.
On the
What's that? Yeah, on the railing of the, yeah, where it sits.
None of our project affects the shuffleboard in any way other than the outer realm of it.
Very well.
Last question.
Oh, yeah, sorry. Here, yeah, guys, there's a lot.
Can you speak a little bit about the image processing that you do to, see the stars, see the colors, and all that stuff? How do you use it?
So the way OpenCV works is that we're using the webcam to effectively take a photo of the board every moment we can. And when it takes the photo of that board, it grayscales it. And using that with ones and zeros and HSV values, it detects what's red and blue, and anything else is seen as black. And once it's done that, it uses a dilate program, which means it takes the kernel that it grabs of a certain size and inflates it to be slightly larger. When it does this to all of them, it creates a slightly larger, we got it set up, it's a slightly larger image. And then once we see enough colors in a certain spot, the area is large enough with those colors. With what we have is going to be 1,000 pixels. Once it's large enough, it draws a box around that shape, and then we use the top left corner of that box that's drawn to determine the coordinates of how up and down it is on the board.
So actually detect only red and blue, right?
Correct. No other colors. There it is! That's the seeds paper we turned in, like, let's go!